All right, hello everyone. In this video, we're going to look at two things: Newton's universal law of gravitation and the equation and derivation of the acceleration due to gravity. So quite simply, Newton's universal law of gravitation says that there is a gravitational force of attraction between any two masses. And that equation can be written this way: Fg, that's the gravitational force of attraction. That's like gravity, the force of gravity. And it's going to be equal to a constant, capital G. That constant is called the universal gravitational constant. And that's the value in the units up here in this box. And it's equal to G times the mass of the first object times the mass of the second object and divided by the distance between them. So many times when we talk about gravity, people think that gravity only acts like down, like the earth pulling me down. But Newton expanded that and said that there's a gravitational force of attraction between any two objects. So we're going to do a quick example here. I'm skipping number 2 temporarily. We're going to look down at number 3. We are going to calculate the gravitational force of attraction between you and your neighbor as you sit in class. So we have two students who are side by side, and we are going to calculate their gravitational force of attraction. So I'm going to write down the equation, and let's plug in some numbers now. So the G is going to be the gravitational constant, and that number is 6.67 times 10 to the minus 11. And then the mass of the first student times the mass of the second student. And I just picked a student who had a weight of approximately 150 pounds, and their mass turned out to be 68 kilograms. So 68 kilograms for the first student, 68 kilograms for the second student, divided by, and then I measured the distance between our desks, and they were about 75 centimeters, but distance has to be in meters. So I changed 75 centimeters into meters and got 0.75, but then we have to square that. All right, so take a minute to pause the video and try to number crunch this in your calculator to make sure that your keystroking is working for you. You should get an answer of 5.48 times 10 to the negative 7 newtons. So yes, you are attracted to your neighbor, but not very much, to the negative 7th power. So your force of attraction is not that large, which is why you're not being like pulled and glued to your neighbor. But now let's shake it up. And let's calculate your force of attraction to a different object. And this time, that object is going to be the Earth. So I'm going to write the equation down. Fg equals the gravitational constant. And when one of the masses is much bigger than the other mass, sometimes we differentiate by using a capital M to stand for like the mass of the Earth. And then the lowercase m will be the mass of you, and then the distance between you. And by the way, when you're finding the gravitational force of attraction between an object like you and the Earth or a planet, that is often called weight. So the gravitational force of attraction between you and the Earth is what you weigh on the Earth. So that's the subtle difference between FW and FG. All right, so one of the things that we have to do is we have to turn each of you and the Earth into a point mass. So I'm going to draw you on the surface of the Earth, so you're going to look like a dot. And now I'm going to turn the Earth into a point mass. And so I'm going to put the point mass like in the middle of the Earth. And so if you look at the distance between your 2 point masses, it's effectively equal to the radius of the Earth. So when I put in my values, I'm going to have 6.67 times 10 to the minus 11, that's the gravitational constant, times the mass of the Earth, and that number is up here in the chart. It's a number we use a lot. You don't have to memorize it, but we'll keep it handy. So 5.98 times 10 to the 24 kilograms. Your mass is assumed to be 68. And now the distance between your 2-point masses is going to be the radius of the Earth. Again, another number that we use often. So that number is up here at the top. And that number is 6.38 times 10 to the 6th. I'm going to parenthesis that because I have to square that. So it's really important that you take the time to put this in your calculator and see what you get when you do your own keystroking. I do admit that sometimes the scientific notation does cause some problems for people. I can tell you in my calculator, I have the greatest success when I put in the first value times this equals divided by, and then I parenthesis this, parenthesis, and then I square that. So take a second and put that in your calculator and let's see what we get. I don't know how well this will project, but we'll try. So I'm going 6.67 EE negative 11. That's the gravitational constant times 5.98 EE to the 24th. Notice I'm not using times 10 times 68 equals. There is my numerator divided by 6.38 EE6. Close my parentheses and I will square that. And my gravitational force of attraction to the Earth is 666.34. 666.34 newtons. Is that a lot? I don't know, but I think it is compared to my gravitational force of attraction to my neighbor, which was to the negative 7th power. So compared to little things, I'm attracted to my calculator, I'm attracted to my car, I'm attracted to my neighbor, I'm attracted to a lot of little things. But I'm attracted to the Earth with a magnitude of 666. So I am most attracted to the Earth over anything else in my local environment, because there's nothing in my local environment that's closer to me and more massive than the Earth. And because the Earth is so much more massive than any other object that you can think of, you will always be more attracted to the Earth. So when I jump up in the air, I don't get sucked to my neighbor. I don't get sucked to my calculator. I get sucked back down to the Earth. And that's why we kind of always think that the gravitational force of attraction is only acting in the down direction, but you're attracted to every object. Okay, so let's now look at, let's kind of like take a more general approach, like Newton might have done. So here's our Earth. There's a lot of objects on the Earth. There's you, there's a dot, there's a car, that's a dot. There's a calculator, that's a dot. Okay, so Newton was thinking, if I'm going to calculate the gravitational force of attraction between each of these individual objects and the Earth, well, the G number is going to be the same. The mass of the Earth is going to be the same. The M of the object is going to be different, but then the radius of the Earth is going to be the same. So the distance is going to be the same. And that distance is going to be the radius. So I'm going to change that to an R. Kind of messy there. But these things are going to be the same. So then if they would be like just faster, if I number crunched the things that were going to be the same, so then I could just multiply the mass times the things that were going to be the same. So I'm going to write down the things that are going to be the same. That's going to be the G, the mass of the Earth, and the radius of the Earth squared in this example. So that would be 6.67 times 10 to the minus 11. That would be the mass of the Earth, 5.98 to the 24th. Divide by the radius of the Earth, 6.38 times 10 to the 6th squared. And we'll number crunch that. 6.67 to the negative 11 times 5.98 to the 24th. And then we'll divide by 6.38 to the 6th squared. And look what we get. What does that round off to be? 9.8. 9.8. So then Newton said, so if you want to know what something weighs at sea level, it's going to be equal to the gravitational force of attraction to the Earth, which is going to be the mass of the object, times all of the things that stay the same, and all of the things that stay the same is G. So we've been kind of like, I'll say, using a shortcut all along that FW equals mg, but that G is the stuff that stays the same. So the acceleration due to gravity equation, G, sometimes written as A with a little g, is equal to the gravitational constant times the mass of a planet or a moon divided by the radius squared of the planet or the moon. And now you can find the acceleration due to gravity of any planet or moon. So for example, let's look at the acceleration due to gravity of the moon. I'm just going to have to plug in the G value. That would be 6.67 times 10 to the negative 11 times the mass of the moon, 7.35 to the 22, divided by the radius of the moon, 1.74 times 10 to the 6th. And then I got to square that. And so you should get 1.62 for the acceleration due to gravity of the moon. And you can also plug in the mass of a planet and the radius of the planet. And using Mars as an example, you should get 3.7 meters per second squared for Mars. I'm going to go back to the first page for a minute. So in summary, the universal law of gravitation is this equation over d squared. Sometimes that distance can be a radius. So it's very common to see that as a radius also. And if one of those m's stands for the Earth, then we can also say it's equal to FW. We can also find the acceleration due to gravity on any large mass by taking the gravitational constant, by multiplying by the mass of the large mass, such as a moon or a planet, and dividing by the radius squared of that moon or that planet. So we'll kind of leave those there as summary statements. All right, so far we have just kind of looked at the equations, and we've been talking about objects that are on the surface of the Earth. So let's now go a little bit higher above the surface of the Earth. So on the Earth, we could have a mountain. I'll draw a little mountain like this. And so at the top of the mountain, gravity could be a little bit less. Gravity is not 9.8 on every single location on the surface of the Earth. It varies a little bit due to hills, valleys, different compositions, but on average, it's 9.8. But I would expect at an extreme location, like at the top of a mountain, that gravity would be less. But we are, for example, we're going to go to the International Space Station, because the International Space Station is about 400,000 meters above the surface of the Earth. So I'm going to put a dot right up here that's going to stand for the International Space Station. So I want you to think about, what do you think the acceleration due to gravity is at the International Space Station? I mean, the people kind of like float around when they're at the International Space Station. Well, let's number crunch and see. So the acceleration due to gravity at the International Space Station is going to be equal to the universal gravitational constant times the mass of the planet that we are measuring with respect to. So that would be the Earth ball. And then divided by, so I got to turn the space station into a dot. I got to turn the Earth into a dot. And so when I measure the distance between these dots, it's going to turn out to be like the radius of the Earth plus the altitude, I'll write that as a distance, that I am above the surface of the Earth. So when I put in my numbers, I'm going to get 6.67 times 10 to the minus 11, mass of the Earth, 5.98 to the 24, divided by, I have the radius of the Earth, 6.38 times 10 to the 6th, plus how high above in meters that it's hovering. So I have to add first, then I have to square. So again, please take the time to put this in your calculator to make sure you're keystroking correctly, and ask your teacher if you're having problems getting the answers out of your calculator. So the acceleration due to gravity at the International Space Station should turn out to be 8.68 meters per second squared. That's kind of a big number. So it's not 9.8. The acceleration due to gravity is definitely less, but maybe not as much less as you thought it might be. Maybe you thought it'd be like close to 0, but it's not. It's 8.68. So why are those astronauts floating around when there's so much gravity at their location? So I want you to think about on the surface of the Earth, where gravity is 9.8. You could jump off a cliff, and while you're falling, you could be floating around, even though there's gravity 9.8 acting on you. And in the International Space Station, and this is better showed when we talk about circular motion, but the International Space Station is kind of like going through projectile motion as it's following the curvature of the Earth, which means it's free falling around the Earth, matching the curvature of the Earth as it orbits. So those people in the International Space Station are in free fall motion, even though there is 8.68 meters per second squared of gravity at their location. So that's just kind of a misconception that many people have. So let's look at an astronaut, and let's pretend he or she has a mass of 68 kilograms. So what would she weigh at the International Space Station? So there's two ways that you could approach this. So one thing that you could do is you could say, well, the weight of something is equal to the gravitational force of attraction to the Earth. So that would be G, the mass of the Earth, the mass of the astronaut, divided by the distance between them. And my numbers would turn out to be 6.67 times 10 to the minus 11. The mass of the Earth would be 5.98 times 10 to the 24. The astronaut has a mass of 68. The distance between them is going to be the same thing here. So that's going to be the radius of the Earth, 6.38 times 10 to the 6th, plus how high up the astronaut is, and then I'm going to square it. And I did that, and my astronaut has a mass of approximately 590 newtons. So that's one way that you could find out the answer. Or you could use the, I'll call it the shortcut. So when we look at the shortcut, we could say, well, the weight of something is equal to the mass times the gravity at that location. So the astronaut has a mass of 68. Gravity at the International Space Station is 8.68. And 68 times 8.68 is about 590 newtons also. So you might say to yourself, well, this way is a lot easier than this way. But if you're not given the 8.68, you would have had to do all of that work in order to get the 8.68. So I kind of think the work is the same either way. But I just want to show you that the gravitational force of attraction, the universal law of gravitation, simplifies to Fw equals mg, as long as you're putting in the acceleration due to gravity above the surface of the Earth. All right, so we just did a couple of examples that showed that our weight will decrease as we go above the surface of the Earth. So what if we go below the surface of the Earth? Many people mistakenly think that if I go closer to the center of the Earth, that I'm going to weigh more. But technically, you're going to weigh less. When you go below the surface of a planet or moon, your weight decreases. Your weight decreases. So the rationale for this is, let's pretend that you went all the way to the center of the Earth ball. So you're all the way at the center. So I turn you into a dot, and then I'm going to turn the Earth into a dot. And if I want to figure out what you weigh, it's going to be equal to the distance between your dot and the Earth's dot, and that distance is 0. And dividing by 0 is not good. And that implies that I'm not going to weigh anything. So at the center of the Earth, I definitely weigh 0. I weigh 0. So why do I weigh less when I start to approach the center of the Earth? So I'm going to put myself halfway down. So this is because of something that Newton called the shell theorem. And the shell theorem says that you are attracted to the mass of the Earth that is below you. So you're attracted to the mass of the Earth sphere that is below you. So when I'm on the surface of the Earth, I am attracted to this entire mass of the Earth. But now if I go into the Earth, let's say I went into a cave and I went this far down, I'm now only going to be attracted to a sphere that's this big. And so it's kind of like the mass of the Earth just shrunk. And if the mass of the Earth just shrunk, then my gravitational force of attraction is going to be less. And as I continue down, the mass of the Earth sphere continues to shrink. And my weight will decrease linearly to 0. So we are supposed to be able to graph this out. I wish I didn't scribble here, but we're going to go below it. All right, we are going to make a graph to show what happens to your weight as you go above and below the surface of the Earth. So I'm going to make a big graph here. And on the y-axis, this is going to be my weight, my gravitational force of attraction, or my weight. And this is going to be the center of the Earth. And this is going to be the distance from the center of the Earth. So I'll call this distance. And you are going to weigh the most when you are on the surface of the Earth. So when you're at the surface of the Earth, how far are you from the center of the Earth? That would be equal to the radius. So I'm going to put that here. I'm going to go out about this far, and I'm going to call this the radius of the Earth. That's where I weigh the most. So I'm going to put a dot like high up on my y-axis. That's where I weigh the most. And so let me kind of correspond that radius of the Earth, kind of make a little circle here. So as I go farther, like up on a mountain or to the International Space Station or to the moon or out in space, and I'm getting farther and farther from the center of the earth, my weight is going to decrease exponentially. How do I know it's going to decrease exponentially? It's because this equation is an inverse square law. When I say inverse square law, that means that there's a 1 over d squared in the equation. So the distance, as the distance gets big, the force is going to get small, but it's actually going to happen exponentially because I have that little squared. So I know the graph's going to look like this. Now, when I go into the earth ball and I start to go deeper, we know our weight is also going to decrease, and it's going to turn out to be 0 when I'm at the center of the earth. So I'm just going to connect these lines, and this shows how my weight will decrease linearly as I go inside a large mass, such as a planet or a moon, something like that. So this is a graph of the gravitational force versus distance, or sometimes called the radius. And it's also an identical graph to the acceleration due to gravity versus the radius, because my weight depends on gravity. And so gravity is going to be the largest at the surface of a planet, and it's also going to decrease as an inverse square law because it's gm over, in this case, an r squared. And it will also decrease linearly as I go inside the planet. Okay, that's a quick overview and review of Newton's universal law of gravitation, and it also led us into the equation for the acceleration due to gravity. I hope that helps, and I'll see you next time.